Welcome back. This is Professor Ridge. Today's lesson 3.4, Composition of Functions. Our first learning objective for today is combine functions using algebraic operations. Combining functions using algebraic operations for two functions, f of x and g of x, with real number outputs, we define new functions f plus g, so the sum of the two functions, or the difference, f minus g, or the product, so f times g, and then the quotient, which is f divided by g. Okay, so we're going to define these new functions. F plus g of x is going to be defined to be f of x plus g of x. Now, if you understand function notation, this should be pretty clear to you. So basically, I always tell my students, this is your first step. You apply the rule. So if you want to add two functions together and create a new function, f plus g of x, you're going to take remember, f of x is the y value for a given x value. G of x is a y value. Okay, the long-winded version. F of x is the y value of the function f for the given x value. So this is the y value that goes with x according to the f function rule, or however you define f. And then this is the y value for the function g for the given x value. So you're going to take those two y values for the given x value and add them together to create the new y value for f plus g. And basically you can do that for add, subtract, multiply, and divide. Okay? So this is the definition of how you add two functions, subtract two functions, multiply, or divide. And basically you're just going to figure out the y value for the f and g and then add, subtract, multiply, or divide those two values. And of course, when you're dividing, division by 0 is not allowed, so you have to add this restriction for the quotient. Example 1, performing algebraic operations on functions. Find and simplify the functions g minus f of x and g divided by f of x, given f of x is x minus 1 and g of x is x squared minus 1. Are they the same function? Okay, let's first figure out the g minus f of x function, see how that's defined. So again, from the definition, from what we just wrote on the previous slide, if we want to subtract two functions, right, you're going to figure out the f of x, the g of x, and subtract them. Now notice this is f minus g. We're doing g minus f, so the order is important. So you got to do g of x minus f of x. And now we're simply going to substitute, well, by the function rule, g of x is equal to x squared minus 1. So we're going to put in the x squared minus 1 for the g of x. And then the f of x is x minus 1. So we're going to put in x minus 1. Now we're going to subtract these two output values, or expressions, I should say. So simplify it, basically. So distribute the negative. So minus, there's two ways to think of it, right? I'm sure I've talked about this before, but just in case. Negative 1 times a is the same thing as the opposite of a. So if this is a parenthesis, negative 1 times, say, x minus 1 is the same thing as opposite of x minus 1. So two ways you can view it. You can think of it as negative 1, so you can think of the minus as negative 1 and distribute it, or you can think of it as the opposite and just change both of these signs. So you're going to do plus, and then change both these signs, so negative x, positive 1, but then you don't need to write that plus, right? So it'll be negative x plus 1. And if you distribute the negative 1, you get the same answer. Negative x, negative times a negative is positive. See, so it doesn't matter which way you do it. All right, so now we're going to combine like terms. We get x squared minus 1 plus 1 cancel, and then minus x. Okay, so that's how we're going to define this new function of g minus f of x is going to be x squared minus x. All right, so now let's do g divided by f. Okay, so let's see, g divided by f, and again we're going to apply the rule. How do you define the quotient of two functions? Well, you're going to take the output value for the top function, so g of x, divided by the output value for the bottom function. And then now simplify that. Well, first we got to substitute in g of x, we know is x squared minus 1. X squared minus 1. And f of x we know is x minus 1. And then simplify this if you can. So I'm going to do factor the top. That's our difference of squares. So hopefully you're getting used to this difference of squares and you can recognize it. So you're going to square root both. So a plus b and then a minus b. Okay. So if it's x squared minus 1, it'll be x plus 1, x minus 1. If it fits this pattern. So we get x plus 1, x minus 1, and then on the bottom we get x minus 1. I'm going to put that in parentheses just to emphasize we're going to cancel the x minus 1, and then we get x plus 1. And that's our final answer for that one. That one. And then are these two functions the same? So you look at those output values and they're totally different. So no, they're not the same. So no, not the same. Oh, and before we move on, I forgot to mention, remember we got to restrict the domain. Anything that would make the bottom here x minus 1 equal to 0, right? You can't allow that to be 0. So x minus 1 cannot equal 0. So x cannot equal 1. So this is the g divided by f provided x is not 1. So if you put in 1, 1 plus 1 would be 2. But you've got to remember what we did originally. And we would get 0 on the bottom, so that would be undefined. Okay, moving on to the next learning objective, create a new function by composition of functions. Okay, so composition of functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x and functions f and g, this action defines a composite function, which we write as f, and then we have this like degree mark, like a small o, but it's not an o, right? So that's the composition. So f composed with g, or you could say the composition of f with g, or the composition of f and g. You could say any of those. Okay, so so this action defines a composite function, which we write as f composed with g, such that f composed with g of x is defined to be f of g of x. So the thing that you got to understand for this notation, right, we're going to plug x, think of it this way, you work from the inside. You're going to take x value, plug it into the g function, and get a y value. That's the g of x, or an output value. Then you take that output value from g, and then you plug it into f to get another output value for the composition. Okay, so you're going to take x, plug it into g, get a value, take that value, plug it into f, and get a new value. And we call this process composition. Okay, so the domain of the composite function f composed with g is all x such that x is in the domain of g and g of x is in the domain of f. So you got to look at that chain of events. So x has to be in the domain of g, and then g of x has to be in the domain of f. Okay, so it's important to realize that the product of functions f times g, that's a different thing. It's not the same thing as the function composition f of g of x, right? So that's not multiplying. This one's composition f times g is basically what we have written here from the example we had a couple ago, right? So f times g of x is f of x times g of x. So you figure out those two separate f and g values and multiply them. Whereas composition, we're taking, one more time, we're taking x, plugging it into g, getting an output value for g, and then you take that value, plug it into f, and get the output value for the composition, okay? Which will give you a different answer like 99.9% of the time, right? So these are not equal to each other. Example 2, determining whether composition of functions is commutative. So if you recall, commutative means you could switch the order and get the same outcome. So we know that like addition and multiplication are commutative. You can switch the order of those and get the same answer with if you're doing with real numbers. Now, subtraction and division are not commutative. So for instance, if you did like 5 minus 3, you get 2, and if you did 3 minus 5, you get negative 2. Okay, but if you're doing addition, 5 plus 3 is 8, and 3 plus 5 is also 8. So the answer is the same. We call this property commutative property, right? So is composition commutative? That's what we want to do. So we want to see if these two compositions, if I do f composed with g of x, and if I do g composed with f of x, do those produce the same outcome? And let's see. So let's start with the f composed with g of x. So we're going to plug x into g first. Well, we're not plugging in any number. So g of x is the 3 minus x. And then we're going to take this expression, this value, and plug it into the f function. So we're going to take this x out. And then we're going to substitute the 3 minus x into it. Okay, so we have the 2x plus 1, 2x plus 1. We take the x out, put in the 3 minus x, and then we simplify this. So distribute the 2. So we get 6 minus 2x plus 1. And then 6 plus 1 would be 6 plus 1 would be 7. And then the minus 2x. All right, now let's switch it around. Let's do g composed with f of x. So we're going to plug x into f. Well, since it's just x, we just write down the expression, 2x plus 1. Oops. 2x plus 1. And then now we're going to do the g function, which is 3 minus x. So again, blank parenthesis. And then I'm going to substitute this expression for the x. Okay, simplify it, so distribute that minus sign. So minus 2x. Again, you can think of it as negative 1 and distribute negative 1, or you can just change both of these signs. So this minus goes away, and then these two change. And then combine like terms. 3 minus 1 is 2. And you can see that these two things are not equal. So in general, f composed with g of x is not equal to g composed with f of x. Now there are some cases where they will be equal, but that's, again, for math, if you say something, if you want a property, it has to be true for all cases, right? So if there's one case where it's not true, then you can't say it has that property. Okay, so again, most functions, f and g, if you do composition and you switch it, you're going to get different outcome. There's some that when you switch it, you'll get the same outcome, but we're not going to worry too much about what causes that. If two functions, we're going to talk about inverse functions later on, and that one of the properties being an inverse function, if you do this composition and switch it, you're going to get the same. You actually get x, right? So for both of them. Example 3, interpreting composite functions. The function c of s gives the number of calories burned completing s sit-ups. And s of t gives the number of sit-ups a person can complete in t minutes. So interpret c, the composition, c of s of 3. Okay, so 3 is the input value for s. So remember, let's see, s of t is the number of sit-ups a person can complete in t minutes. So 3 is t, which is 3 minutes. Okay, and then you're going to plug, so you're going to plug 3 into the function s of t, and let's say that gives you, for that person they can do 60 sit-ups, right, in 3 minutes. And then you're going to take that answer, that's 60, and you're going to plug it into c, and c of s is the number of calories burned completing s sit-ups. So if it, say it was 60, then c of 60 would be, I don't know, you burn 25 calories or something, right? So then we're going to take, so s of 3 is the number of sit-ups. In 3 minutes. And then we're going to take that answer and plug it into here. So that's the number of calories burned completing whatever s of 3, so if that's 60 sit-ups. Okay. I should also mention, right, so this is the input value for the composite function. This is the input value, 3 minutes, and the output value is number of calories burned. So c of s of 3 is going to be the number of calories burned, okay, is the output value. So just kind of emphasize that. So the minutes, the number, so this is basically tells you the number of calories burned for 3 minutes. Okay, the next learning objective, evaluate composite functions. Example 5, using a table to evaluate a composite function. Using table 1, which is right here, evaluate f of g of 3. So we want this composition. And then also do g of f of 3. Okay, so we're going to, let's start with the f of g of 3. So again, if you understand the function notation, this should be a piece of cake. So g of 3, remember, this is the output value for the function g when x is 3. So we're going to go to x is 3, and then g of 3, the output value is going to be 2. So we're going to take the g of 3 out and replace it with 2. So that's going to be f of 2. And then we're going to take the 2 and plug it into f and get the output value for f when x is 2. So then we go to 2 here on the table, and then we go to this column. We want to know what f of 2 is. So f of 2 is 8. So f composed with g of 3, or f of g of 3, is 8. Okay, so that's that one. Now let's do g of f of 3, and you're going to, well, I don't know if they're going to be the same or different. Generally they're going to be different, but sometimes they're the same. Okay, so now again we're going to start with the f. You start inside. X is 3, we're plugging it into the f function. So what's the output value for f when x is 3? So again, you go to x is 3, and you go to the f function. The output value is 3 again. So this would be g of, so we take f of 3 out and replace it with the f of 3, which is 3. Then we're going to take the 3 and plug it into g to get the final output value for the composition. So we're going to go to 3 again here, and then we take 3, plug it into the g function. The output value is 2. And you see, yeah, these give you different results. Okay, so the order matters. So you work inside out when you do composition. You start, this is your input value, plug it into G, get an output value. Take that output value, plug it into F to get your final answer. Okay, and then this one, we're going to start with the 3, plug it into F, get an output value for F of 3, which is 3. And take that answer, plug it into G to get your final answer. Okay, so it's, you're putting one function into the other function. Right, that's composition. Example 6, use a graph to evaluate a composite function. So here's the technique. You're going to locate the given input to the inner function. Remember, we start inside out on the x-axis graph. Read off the output of the inner function from the y-axis of the graph. Then you're going to locate the inner function output on the x-axis of the graph of the other function, and then read the output of the outer function from the y-axis of its graph. This is the output of the composite function. Okay, so that may be a little confusing when you read it. Let me just kind of go through it again the way I would do it. So again, we're going to start with the x, right? And we're putting it into the g function first. So here we got f and g. So this one's F, this one's G. They were nice to you, put it in order for the way you're going to do it. That may or may not be true on the exercises, so just pay attention. So we're going to take the 1, plug it into the G. So we're going to go for the G function, go to x is 1. Here, let me change this to red. Actually, let me do it as a line. I'll do a dotted line. So we go to x is 1. You see that comes up to here, and then we're going to read off what the y value is there. So for g of 1 is equal to 3. So we're going to take this g of 1 out and put in 3 there. So f of g of 1 is equal to f of 3. Now we're going to go to the f function, which is this one. We're going to do the same thing. We're going to do the x is 3. We're going to go up to the graph here, and then we're going to go over, and you can see that's going to be 6. So then f of g of 3 is going to be, so f of 3 is 6. So the composition f of g of 1 is equal to 6. Okay? So that's pretty much what this was saying. All right, so you're going to plug the 1 into g first. So you go to the graph, x is 1. You go to where that grid line intersects the graph, and then read off the y value. So g of 1 is 3. Now you take that 3 and plug it into that function. So you go to x is 3 on the f graph, go up, it intersects the graph right there. So what's the y coordinate for that point? So you read off 6. Hopefully that makes sense. Evaluating composite functions using formulas. how to. Given a formula for a composite function, evaluate the function. So your first step is evaluate the inside function. Remember, we work inside out for composition of functions. Okay, so evaluate the inside function using the input value or variable provided, or it could be an expression like we did earlier. Use the resulting output as the input to the outside function. Okay, so we're going to start with, let's see here, given f of t is t squared minus t, and h of x is 3x plus 2, evaluate f of h of 1. So f of h of 1, we're going to plug 1 into the h function first. So there's two ways you could do this. Sometimes I'd say, all right, let's just on scratch work figure out h of 1. Right? So h of 1 using this formula here is 3x plus 2. So I take the x out, put in the 1. Right? So you got 3x plus 2. So h of 1 is going to be 3 times 1, which is 3, and then 3 plus 2 is 5. So h of 1 is 5, so now I can substitute h of 1 and put 5 in that spot. Now to simplify this, I'm going to take the 5 and plug it into the f. So f of 5, I'm going to use the f function, which is t squared, so I take the t out, put a blank parenthesis, minus t, put a parenthesis there, and then substitute 5 for all those blank parentheses, and then work this out. 25 minus 5, which is 20. So my composition will be f of h of 1 is equal to 20. Now, I was saying there's a couple ways I could do it. The other way I could do it is I could just do all this work right inside the problem. So instead of doing this, I would have showed all this work here inside the parenthesis. So I would have done something like f of h of 1 would be 3 times 1 plus 2. And then probably not show any work here, just type this in my calculator and then get the f of 5. And then from there, just show this right in the problem, right? So you can do it either way, whichever makes more sense to you. I think for most students, when I first show it to them, they like to do it separately, like I did over here in scratch work. Okay, so but that's up to you. Okay, the next learning objective, find the domain of a composite function. Domain of a composite function. The domain of a composite function, f composed with g of x, or just f of g of x, is the set of those inputs x in the domain of g for which g of x is in the domain of f. So here's the technique. You're going to find the domain of g first, right? You start on the inside. So what x values are you allowed to start this kind of, you can think of it as like a chain reaction. So what x's are you allowed to put into g? So that's the domain of g. And then those, when you plug it into g, you get outputs, right? Now, your next step, okay, so hold that thought for a second. So you're going to figure out the domain of g. Then you're going to find the domain of f. For those inputs x in the domain of g, for which g of x is in the domain of f, that is, exclude those inputs x from the domain of g, for which g of x is not in the domain of f. The resulting set is the domain of f composed with g. Okay, so we'll do an example and I'll kind of explain that. Example 8, finding the domain of a composite function. Find the domain of f composed with g of x, where f of x is equal to 5 over x minus 1, and g of x is 4 over 3x minus 2. So our first step is figure out the domain of g, because we're going to start at the inside. So the domain of g now remember, if you have a fraction, the bottom's not allowed to be equal to 0. So we got to exclude whatever makes the bottom equal to 0. So we get 3x, we add 2. Oh, we got to exclude it, so you can put not equal to. And then divide by 3. So x is 2/3. Or is not equal to 2/3. So our domain for G would be all real numbers except 2/3. Okay? 2. Then we're going to find the domain of F. So again, if you have a fraction, the bottom's not allowed to equal to 0. And then you solve that. So add 1. Okay. Okay, so let's look at this how-to again. So we found the domain of G. We found the domain of F. Now find those inputs x in the domain of G. So we're going to go back to the domain of G. And then for which G of x is in the domain of F. That is, exclude the x's from the domain of G for which G of x is not in the domain of F. The resulting set is the domain of F composed with G. So what we're going to do is we're going to use this domain. So from negative infinity to 2/3. Oops, I don't know what I did there. Union 2/3 to infinity. And then we're not going to exclude x is equal to 1. We're going to exclude exclude G of x. We're going to that equals 1, right? So G of x, because that's what's going in here, we're going to do G of x. So G of x is this one, and we have to solve it for what makes that equal to 1. So we're going to cross multiply. I don't know if you know that technique. So 4 times 1 is 4, and then 3x minus 2. So basically I cross multiply. You can do that if it's a fraction equals a fraction. Okay, and then we solve this one, and we're going to exclude this number. So we get 3x is 6, and then divide by 3. So x is 2. So you got to exclude 2 from the domain of G in addition to things that you excluded from G, right? So we're going to take this and throw out, this is going to create another whole, if you think of the number line, from G we took out 2/3 and we excluded that. And now from this one, F, x is not allowed to be 1, but we got to remember we're doing this composition, so G of x can't be 1, right? So I should put not equal to 1. And so G of 2 will get you 1, so you got to throw that one out. So now our domain for the composition is these 3 pieces. So negative infinity 2/3, and then so the domain of F composed with G is equal to negative infinity to 2/3 union 2/3 to, so this middle piece, 2/3 to 2 union, and then this, the right piece, 2 to infinity, 2 to infinity. And that will be my answer right there. Okay. Example 9. Find the domain of a composite function involving radicals. Find the domain of f composed with g of x, where f of x is square root of x plus 2, and g of x is equal to 3 minus x. Alright, so let's start with, we're working inside, so we start with the domain of G. So domain of G. So remember, if you have a even root, so square root, fourth root, sixth root, the radicand, the number inside, has to be greater than or equal to 0. So that's our domain. So we solve this. So we subtract 3 from both sides, divide by -1. And again, I want to point out, if you divide both sides by a negative, you got to flip the inequality sign. So x is greater than 3. Then we look at the outside function, f. So what's the domain of f? And domain of f is square root. So again, it's a root, so the radicand has to be positive, or 0, has to be non-negative, so greater than or equal to 0. Subtract 2. But remember, we're doing composition, so this has to be g of x has to be greater than -2. Well, g of x is square root of 3 minus x, which is greater than or equal to -2. Now, for this one, basically, when you take the square root of this, anything that's in the domain of g that makes this a real number, when you square root it, it's going to be positive. So the domain for this function will actually be, because see, if you square both sides, you get 4. And then, let's see, so basically the domain here is going to be all real numbers well, not all real numbers, but all real numbers that are in the domain of G, right? So anything that's going to make this true will make this statement true. So that's a little confusing, but your domain of your f plus g, or f composed with g, is equal to just the same domain here, which is -infinity to 3. Right? Okay, and our last learning objective for today, decompose a composite function into its component functions. Decomposing a composite function into its component functions, so I wanted to point out, the book says here, in some cases it's necessary to decompose a complicated function. In other words, we can write it as a composition of two simpler functions. There may be more, this is the key thing, right? There's more than one way to do it. There may be more than one way to decompose a composite function, so we may choose the decomposition that appears to be the most expedient. So for instance, if we took a function, say f of x is equal to, say, x plus 3, and g of x is equal to 2x. And if I did f compose with g of x, that's going to get me f of g of x, which g of x is the 2x, and then I'm going to plug it into the f, so that'll get me 2x plus 3. So if I want to take this function and decompose it, I can say I can think of it as like order of operations, right? If I have a number for x, I'm going to multiply it by 2 and then add 3. Multiply by 2 and then add 3. Okay? So these are my two. I can take this function, this is a real simple case, and decompose it into the two separate functions of multiplying by 2 and adding 3. And we remember, we go inside out, so order operations, we're going to multiply first by 2, so that'll be my g of x, and then we add 3, that'll be my f of x, right? So that's one way to do it. There's several, there's not several, but there's a few different ways that we could do this. Another thing is if you see grouping symbols, So like the square root is a grouping symbol. I can call that what I call my inside function. So that'll be my g of x will be the square root. And then whatever's under that in the grouping symbol, in this case in the square root, the radicand, that'll be my f of x. Okay, so, well, this is called f of x. So we're going to do f of x is, we're going to do a composition of, say, f of x is going to be g composed with h of x. So my inside function will be the let's see, how do I do it? So the square root's going to be my grouping symbol, okay, and then what's inside that, that's going to be the inside function. So that'll be my h of x. So we're going to let h of x be the 5 minus x squared, and then we're going to let the g of x be, now here's what I tell my students, just we're going backwards. So typically when we do composition, we take, if we're going to plug 2x into f of x, we take the x out and replace it with the 2x, right? So we're going backwards, so we're going to replace the 5 minus x squared and reset it to x. So we're going to take the 5 minus x squared and replace it with just x. So my g of x is going to be the square root of x. Okay, so that's, I think that's the easiest way to view it. So again, you're going to have the inside function. So the inside function is going to be what's inside the grouping symbol, 5 minus x squared. And then the outside function would be whatever, you're going to replace the, whatever you set as your inside function, replace it with x. And then the outside function would be just whatever's left over when you replace. So we're going to take this whole thing here and just replace it with an x. So it'll be square root of x. Okay, so hopefully that makes sense. I think that's the easiest way to view those. Okay, let's go ahead and check it just to make sure. So see, h of x is going to be, so here's my check. H of x is the 5 minus x squared. And then I'm going to take this and plug it into g. So I take the x out and put in the 5 minus x squared. And then we get the original function. Okay, so that's how we can decompose it into component functions. Okay, that brings us to the end of the lesson. So again, practice, practice, practice. Do a whole bunch of exercises, minimum all the odd problems in the exercise set, and I will see you next time.